that on that. Okay, so I go, I need to use my little flip it thing that I wrote down and told you it was useful. Okay. So I want to demonstrate that this statement, this lack of conditional dependence, this independent probability idea goes both ways. I mean, it flips across to the other way. So I can't just go down to the intersection like I did here and say this equals that, B, A. Oh, no, because I'm not assuming that. Sorry. So, probability of A intersect B over probability of A, and this is this. So if I take this thing here, B, let's see, probability of B. If I was just a tiny little bit smarter, this would take less time. Okay, where am I at? So intersection, probability of B, I want the B down there. Christ. But that's all screwed up. Alright, I'm going to stop wasting time. Where is it? Okay. A given B times B. Probability of A given B. Probability of A given B times B. That's probability of B equals probability of B given A times probability of A. That's what my flipping around probability thing is. And B given A given B. So then, I know that's true. Oh, okay. So I got, so I can take this probability of A given B, stuff it in right there, probability of A given B. And then I got that go away. And I have cleverly derived that the probability of A given B equals probability of A implies both directions, actually. The flip is true. So if A, the only thing that says is that that independence is not an ordered pair. A and B are statistically independent. Means that B and A are statistically independent. It doesn't, it's just the pair. It doesn't matter which one you're looking at. That's all, nothing more. And then, very often we talk statistics about, oh, how many n different IID random variables you can dream of. So, just jump ahead a bit. If I say I have a sample from a normal population, a standard normal distribution, 0, 1, Gaussian Z statistic check. If I have a sample and I call that x1, just random sample, and then I again randomly sample. It's not as easy as saying it. Call that x2. Is x1 and x2 are random variables which express some outcome, and a random variable is a function. It maps you between outcomes to an expression of a probability distribution. Anyway, x1 is a sample from a z distribution. x1 will follow this distribution. That is what it is. So the distribution of x1 is z is equal to the distribution that we use random variable z to commonly say. I don't think I can even write the function anymore. 1 over root 2 pi something e. Let's see, we're going to have a x squared and some pi, something stuff, and a negative sign. Outside of that, because you don't care about which direction, it's symmetric on 0. Okay, that's the function f of x that gives you the bell curve. This thing can be a sample from a random sample from the z distribution. And this thing also is some generic, whatever, random sample that follows the z distribution. And because these things were sampled in the way that you do statistical sampling, correct, proper sampling, they are sampled to avoid any dependency. They are independent samples. And that's what, that's kind of the critical assumption in a lot of this work you do. You have X being IID, normal, whatever, X of I. You have a set of random variables, x1 through xn. that represent your sample. And they are identically, independently distributed like that. You get into problems very, very quickly. Very devastating problems very quickly if you have a lot of dependency in your sampling. This happened with, the phone book sampling. I won't go into that. Okay. This isn't sampling. Okay. That was just a little foreshadow. Dice. I want to do that.
5:16.
All right, we'll go a little more. Okay, dice. A die is the cube that you use when you play some game. Dice is more than one die. So there are 6 outcomes. The outcome is dots, unless maybe listed number. But you can express it like 1 dot, 2 dots, 3 dots, 4 dots, and you can say that there's 1/6 a chance of that. 1/6, 1/6, 1/6. We know that those are probability 1/6 because it has to add up to 1, and you have 6 things, and there's no way to say that one of those sides is more probable than another, unless you buy your dice from the right place. And you can buy dice and try to make money with dice that are not fair. But we assume fair dice. And just by saying it is, there's no way that any one thing is more likely than another thing, then they must all be equal, and you have this. So we can have outcome D expressed as dots, and this random variable function is what maps it over to something that's like 1, 2, 3, 4, 5, 6 with probabilities. But you don't need to think much about that. I don't want to give thick definition stuff. Okay. I have some events examples here. We have, he said x1 is the symbol, the random variable, to represent the outcome of a single roll. So this thing takes values from in the set 1, 2, 3, 4, 5, 6. These are the possible values of the random outcome. You cannot roll a die, and get 7. Okay, the probability that, notation, okay, how do you write it? Random variable, probability that x1 equals little x value is the function, you can write a function f of little x, and this is takes on the value 1/6 for the space of x's in the set 1, 2, 3, 4, 5, 6. If x is 1, the probability is 1/6. If x is 47, the probability is 0. Because it can't happen with a die. Unless you want to have fun with complex numbers for probabilities. Okay, that's just how we write it. Which is also, I can write this function as x, f of x, 1, 2, 3, 4, 5, 6, 1, 6, 1, 6, 1, 6. Okay. Random verb, 1 repetition, probably won't say. X is not in there. Okay. Right, so I can say, I can write this probability of x1, the random variable, taking on the value 1. Now it's a number. I don't have a function, I have a number. So to compute 1/6. Now, just plain. Now I talk about events. Events are kind of like random variables. Event A, I define as outcome of being a 1. B is the event which is true. B is true for outcome of random variable x1 is 2. I define event C as x1 being less than 4. I define it now 1, right? D is x1 is odd. That's 1, 3, 5. Alright. So, probability of A is the probability that x1, that's the outcome of the dice, the number that is rolled on the first roll. Probability of A is the probability that x1 comes out to a 1, which is 1/6. That's 1/6. This, the probability of C is the probability that x1 is less than 4. x1 is less than 4, has 0 probability in general, but it has 1/6 at 1, and it has 1/6 at 2, and 1/6 at 3, and 0 everywhere else. Like negative infinity, 0 probability. So this is the probability, this is just a way of saying the probability that x1 is within the set 1, 2, 3. So it's half, right? It's the lower half. 1, 6, 1, 6, 1, 6. So this is probability of C is 1/2. The same is true for event or D. Probability of event D is the probability of an odd number, the probability of a 1, a 3, or a 5. They're all equally likely. It's half the space. Probability of D equals 1/2. I'm relying on that being obvious. So then what the hell do I do with that? One would think that I did some conditional probability stuff. Like, I don't know, maybe not. Like, this is impossible. Like, the probability of A given B. What the hell does that mean? Well, that means the probability of A intersect probability of B intersect B divided by probability of B. I still don't know what that means. Probability of B, I know that's 1/6. But the probability of this intersection is the probability of A and B being true, which is the probability that I roll the single die and I get 2 results. And that can't happen. I roll it once. I have 1 result, I don't have 2. So this is 0. The probability of getting a 1, if you know that you got a 2, is 0. It seems stupid, but it's good to just see these little things. That these are mutually exclusive. That's the other explanation. I mean, the intersection of the event space is 0. It is the empty set. There is nothing in this intersection. If that was a 1, then they're the same thing and there isn't it. Okay. Yeah, okay. We will stop and for a break, 15 minutes, when we, let's see, I show Cinque Media, 15 minutes, quarter till,
6.
Quarta a las 6.